Hello, class. In this video, we're going to officially talk about what on earth a generating function is and how this is possibly going to get us some interesting combinatorial results. Okay, so I'll note for some combinatorialists, generating functions are their bread and butter. They're how they immediately approach everything. And almost everything we've proven this semester, you could go back and you could prove from the point of view of generating functions. Whereas from the point of view that I've given you so far, we've sort of strived to use combinatorial proofs where we've explained stuff explicitly in terms of counting. And so from the point of view of combinatorialists who try and take that view, these things are completely cheating because we're going to very rapidly run into talking about functions from calculus that don't have any combinatorial interpretation. Okay. So you can think of these as in some way analogous to mathematical induction, where you can give proofs of things, but maybe your proof answers, okay, this thing is definitely true, which is half of what a proof does. But very often these proofs that we're going to give using generating functions won't give a lot of insight into why the thing is true. Okay. And that's really interesting, and we'll talk about that more as we delve into some examples. Okay. But the heart of all of this goes back to this thing called Maclaurin's theorem. Okay. And Maclaurin's theorem is this theorem from Calculus 1. It's a special case of Taylor's theorem, which says that if f is nice enough, okay, and so here that f is some function in the calculus-y sense, so it's some function from the reals to the reals, and like in any calculus thing, maybe it's not defined at all, the reals, but it better at least be defined at 0. Then if x is nice enough, f of x is equal to the sum as k goes from 0 to infinity of the kth derivative at 0 of f over k factorial times x to the k. This is what Maclaurin's theorem said. And so this got you a bunch of things like we already actually have used when we were talking about derangements and permutations. This theorem, or the application of this theorem to e to the x, which is that this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Note, this is one place where it's really convenient to let 0 factorial be 1, because otherwise you have to separately specify what the constant term of this thing is. Okay, but what this theorem really is, if you think about it at the end of the day, is it's sort of a dictionary that relates 3 different concepts. Okay. So on one hand, we have a sequence of coefficients. Okay, and so a sequence is just a function from the positive integers or the non-negative integers, probably, to the reals or the complexes or the integers or whatever you want. It's just a list. Okay, that's one of the boxes. Okay. On the other hand, we have power series. So these are those things that look like, okay, some number a0 plus some number times x plus some number times x squared plus dot dot dot. So that's our power series. And finally, we have our calculus-y functions. Okay, and by calculus-y functions, I mean that we're not overly concerned about exactly where these things are defined, but that there's some nice coherent formula for them, like e to the x, or sine of x, or 1 over 1 minus x squared, or whatever it happens to be. Okay. And basically, the whole idea of this circle of thought around Maclaurin's theorem is that, hey, I can translate back and forth between all of these. And so all of these things are connected. And it doesn't take a ton of thinking to realize that this box up here, this sequence of sequence of things, one for each positive integer, this is what combinatorics is basically about, is about these sequences. And so basically the idea of generating functions is to turn combinatorially significant sequences into power series, and then use those power series to think about those things as functions. Maybe you can write them in some nice way. I'll give you some examples of that. And then use the calculus stuff that we know about functions to then sort of feed stuff backwards and to eventually say stuff about the sequence itself. Okay, so I want to give you some examples of what this looks like. And I will give you a number of examples, and basically this whole week is going to be examples of things of this flavor. But let's start with the simplest sequence that you could possibly start with. So let's start with the sequence 1, 1, 1, 1, 1, and a bunch of 1s. Okay, so that's my sequence. Okay. This sequence gets translated to a power series, and the way it gets translated to a power series is you literally just throw these things in front of powers of x and stick plus signs in front of them. So it gets translated to 1 plus x squared plus x cubed plus dot dot dot. Okay. And this now, I can think of this as a function, and the way I think about this as a function is I think, okay, so if I plugged in an x here, you might realize that this is a geometric series, and so you might even have words floating around in your mind like, okay, so this is a geometric series, this converges for x whose absolute value is less than 1, and then the thing it converges to is in fact 1 over 1 minus x when it converges. Okay, so in some very specific sense, we have linked this sequence, which admittedly is a pretty boring sequence, but we'll do more exciting examples later. We've linked this sequence with this function. Okay. And so as soon as we link this sequence with this function, we can do all sorts of fun things, like take its derivative, take its integral, add it to other functions, all of these sorts of things. So all of calculus is now sort of ready to sort of throw at this function. Okay. Now, let's try and do a different example. Okay. Namely, let's take maybe the second simplest sequence I can think of. Okay, maybe third, because maybe 0, 0, 0 was the easiest sequence, but that one was kind of boring, so we're not going to talk about that one. Let's take the sequence 0, 1, 2, 3, 4, 5, dot, dot, dot. Okay. And so this gets translated to 0 plus x plus 2x squared plus 3x cubed plus 4x to the fourth, plus dot, 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 like that. And what does this get translated to? Well, this is a function now, and because you can figure out, like, what kind of function is it. In fact, it's the function g of x equals x over 1 minus x squared. Okay. Now, I'll note this arrow here, this is completely trivial. This arrow is less so. How on earth did I get from here to here? Okay, what is the secret? How did I do that? Okay. And the answer is actually going to come back to this one. In fact, almost everything we're going to do with power series in this course is going to come back to this specific power series. And so here's one thing you might do. You might say, okay, I've got the sequence that corresponds to this 1 plus x squared plus x cubed plus blah, blah, blah. And I know that that corresponds to this function. And so what that means is the derivative of this sequence, the derivative of this power series must correspond to the derivative of this function. Okay. And so what is the derivative of 1 plus x squared plus x cubed plus blah, blah, blah? Well, we can figure that out. So I'm going to go ahead and give this a name. And this is what I'm usually going to do when I'm doing this. I'm going to call the function by a little f name and the power series, the function by a little letter name and the power series by a big letter name. Okay, so that'll be my f of x. And so my f prime of x, or remember, this is just literally the derivative of this power series, which is basically just a polynomial. So the derivative of that is 0, plus the derivative of that is 1, plus 2x, plus 3x squared, plus 4x cubed, plus blah, blah, blah. Okay. That's my derivative. Okay. And so what function is that associated with? Well, that's associated then with the function little f prime. Okay. So this is the derivative of 1 over 1 minus x. Okay. So the derivative of 1 over 1 minus x, this is the same thing, by the way, as 1 minus x to the minus 1. So its derivative is you pull down a minus 1 times 1 minus x, subtract 1 from the power, and then don't forget the chain rule, as I've been telling my 141 students lately. We multiply by the derivative of the inside piece, and so the point is these two minus 1s cancel, and I get 1 over 1 minus x squared. And so in this trifecta here, the function that goes with this power series is 1 over 1 minus x squared. Okay. And likewise, the sequence that this is associated with would be the sequence 1, 2, 3, 4, and so on. Okay. So all of these pieces, again, we have a sequence, we have a function, we have a power series. They're all sort of different ways of communicating the same information. Okay. But the example I said we would get to was this one. Okay. And you'll notice the power series that goes with this is a little different than the power series of the thing we have. Okay. Namely, the powers of x are off. But having the powers of x not line up is probably the easiest problem you can have, because if you want to line them up, you just have to multiply by the right power of x. Okay. Namely, to get from here to here, what do I have to do? Well, I have to multiply this power series that I have up here by x. And so then I'll get x plus 2x squared plus 3x cubed plus 4x to the fourth, and so on. I'll get this. So, namely, this power series here, it is x times f prime of x. Sorry, there's a prime there that did not show up super well. Okay. And so that means this g of x that I'm looking for, it's got to be x times little f prime of x. But little f prime of x, that was 1 over 1 minus x, little f prime of x, that was 1 over 1 minus x squared. So that means that my function here is, in fact, exactly as I claimed, this x over 1 minus x squared. Okay, so that is this example. Already, this is getting a little bit complicated, but we sort of see that yes, every sequence that we write down, or at least most sequences that we write down, I'll talk about that in a second, will correspond to a power series, which will correspond to a function, and then we can somehow figure out how to translate between them. But notice, going from the power series to the function that represents it is a bit of an ad hoc process. I sort of just did some stuff and eventually got this. It'll require trial and error to figure out in any particular instance. Okay. So I want to do another example where I'm going to start with a sequence, and I'm going to start with a sequence that we know well, and then I'm going to figure out how I would write that down as a function. So I'm going to choose some positive integer n, and my sequence here is going to be n choose 0, n choose 1, n choose 2, and so on down the line forever. Okay. So that's going to correspond to the power series, n choose 0 plus n choose 1x plus n choose 2x squared plus dot dot dot. Which would maybe, if you wanted, you could write this as the sum as k goes from 0 to infinity of n choose k times x to the k. Okay. Which might look familiar, namely this should be exactly what you get from the binomial theorem. Now you might have one critique about how this relates to the binomial theorem, namely you might critique this infinity here. But this would be exactly the same if I took the sum from 0 and I actually stopped at n. And the reason for that is as soon as k is bigger than n, it's no longer possible to choose k things out of n things, and so all these coefficients become 0. Okay, and so the sequence I wrote down originally, it is an infinite sequence, but at some point everything from there on is 0. Okay. But the binomial theorem explicitly tells us how to write this information as a function. Namely, we write this information as a function as little f of x equals 1 plus x to the nth power. And so, in fact, the binomial theorem, we could think of it as very explicitly telling us what the generating function is for this particular sequence. Namely, the binomial theorem tells us that the generating function for the sequence of n choose something is exactly the function 1 plus x to the n. That's this polynomial. Okay. Now, any combinatorial sequence we've talked about so far, you could attempt to do this with. Okay. And so, just to give you an example that this really does work even for some quite complicated things, you might remember we talked about these things called the Catalan numbers. Okay, and so the Catalan numbers, their sequence went like this. Okay, and you might remember these are the number of lattice paths from 0, 0 to nn that stay entirely above this diagonal. So we wrote down pictures of that sort or whatever. And so we counted those, and we eventually came up with this formula that the nth Catalan number was 1 over n plus 1 times 2n choose n. Okay, which is a little bit messy, and the proof was also a little bit messy, but we eventually got there that this is exactly the number of such paths, and then we talked about how, actually there's tons of different counting problems to which this is the answer, and so these things are the special numbers known as the Catalan numbers. Well, it's no secret how to turn these into a power series. Will look like this. Okay, and again, this power series is really coherently telling you the third Catalan number is 5, the fourth Catalan number is 14, and so on. It's just encoding very explicitly what all of the Catalan numbers are. And notice, because we generally associate constants with an x to the 0th, it's going to be natural for us to start counting at 0. And so we're here saying the 0th Catalan number is 1. Now, I won't go into a proof of this, but you can actually show that if you want to write this power series as a function, it actually comes out to be the function exactly this. So again, there's a relatively nice function that gives you this. And in fact, actually, if you're interested, you can go on the Wikipedia page for the Catalan numbers, for example, and you can see this proof. You can actually derive this formula that we derived in a fairly straightforward way by first proving that this is a formula for the that this is a formula for the power series of the Catalan numbers, and then deriving that formula as a consequence of that. Okay. The reason I'm not going to do that is because it runs through something called Newton's binomial theorem, which we've mentioned before is the version of the binomial theorem where we have to use non-integer powers. So in this case, you have to use a 1/2 power to expand the square root here. And so we're just going to skip that. But it's a neat thing. If you want to read about it, it's not too complicated, and it's fairly interesting. Okay. I do want to note that not every sequence that we've considered so far does this work for. Okay. And so here's one very basic sequence that we've thought about a lot. Namely, we've thought a lot about the factorials. So the list 1, 1, 2, 6, 24, 120, blah, blah, blah. Okay, so this would translate to the power series 1 plus x plus 2x squared plus 6x cubed plus 24x to the 4th plus blah, blah, blah. Okay. Again, every time you see a power series like this, you should be thinking of it as, in our case, when it's a generating function, you should be thinking of this as saying the 4th factorial is 24, the 3rd factorial is 6, and so on. So every term of this is explicitly telling you one of the terms in the sequence, and it's even telling you which one in the exponent. Okay, so the way we would go about translating this to a function again is by figuring out, okay, if I plug in some values of x, what function does this behave like? And now here's a problem, and I'm mostly not going to talk about this problem again, but I wanted to at least point it out. If you go back to your Calculus 2, you might recall thinking about power series and the ratio test and something called the radius of convergence, and you would figure out which the x's were where this thing actually converged. And all that you really need in order to make sense of this whole idea of getting a function here is for this to converge for infinitely many values of x, which all the previous ones do. Okay. But actually, because factorials get so big so quickly, if you think about it, like by the time I get to x to the 10th, it's got a 10 factorial in front of it, and 10 factorial is a ridiculously huge number. That means that this power series is actually going to converge for very few values of x. In fact, this power series converges exactly when x is 0. So if and only if x equals 0. Okay. So the quote-unquote function that this is associated with is just the function that sends the number 0 to the number 1, and it contains no other information. And so that's definitely not anywhere near enough to boil out this sequence. Okay. And so the moral here of the story is that this only works. Okay, and by this, I mean using generating functions to associate a sequence of numbers to a function. This only works if what's called the radius of convergence of the power series is greater than 0. Okay. And the radius of convergence is just telling you, if you're thinking about stuff on a number line, you're starting at 0, how far can I go to the left and right while still having this thing converge? As soon as I can go even like 0.0001 away from 0, that's plenty. It gives me definitely infinitely many values, which in fact uncountably many values if you want to think about that. And so that gives me way more than enough information to completely recover the sequence that I started with. But when your sequence grows super, super, super fast, like the factorials, then the radius of convergence actually is 0, which is what this statement is saying, and then you can't get any information. Okay, so really what you need is you need your functions that you're going to be looking at to grow, quote unquote, sub-exponentially in order for this to work. But I'm just not going to talk about issues again where this is a problem. But you might think about this occasionally when you need to think about convergence. Okay. All right. So that was a longer one than I intended, but that gives us an idea of at least how generating functions work, what they are. Namely, they're a way of translating any sequence of positive integers, or actually real numbers of any flavor, but they're usually going to be answers to counting problems, so they're typically going to be positive integers in our case, to some function from calculus. And then we have yet to see how that could actually be useful. But in the next video, we'll go ahead and we'll talk more about how we can usefully use things that we know from calculus in order to answer questions about sequences. Until next time, stay well.